Hi, so for my final project, I made Virtual Archery, which is an iOS archery game that allows you to use physical gestures to draw and shoot arrows. And in addition, you can use speech commands to control the game. The system responds by rendering 3D graphics, having sound effects and spoken audio, as well as providing haptic feedback. And so we can jump into a demo here. And I can first show speech commands, so I can say something like move the target. Okay, and the target readjusts. And we can enter firing mode by pressing the volume button. And I can draw my hand back. And when I open it, we'll fire.
That is 9 points.
Okay, and I can do that one more time, so I can take it back.
You scored 10 more points.
Right, and I can show that how close you are to the actual device, how close your hand is, matters in terms of how hard the arrow shoots. So if I do it one more, I keep my hand pretty close.
That is a miss.
You can see that the arrow dives down. And so now I'd like to talk about how all of this works. So yeah.
All right, so how does this system all come together on device? We're going to need the front-facing camera up here, and every frame or every 1/24th of a second, that image is going to go to two different networks. One is the depth network. It's going to judge how far back you're currently drawing your arm between 0 and 1. And that's going to give the system an idea of how much velocity the arrow should have when it's released. The other network's the gesture network. That network's detecting open or closed hands if you're still drawing or if you're firing, as well as if there's no hand in the image at all. And so these networks are loosely based on VGG16 with this series of pools and convolutions. They're built in Keras with the TensorFlow backend, and they're transferred natively to iOS with CoreML. The depth network was trained on 1,800 512 by 512 images. They were hand-gathered from 8 different participants, and they were also hand-labeled. That network is trained to do regression with a mean squared error loss. The data kind of looks like this. You can see there are some labeled images here, and the idea is that the network would be able to learn this kind of continuous output space given kind of some of these discrete values going into the system. The gesture network, on the other hand, is just doing straight classification. It has more samples with 3,500 from the same participants, and it's trained on categorical cross-entropy loss. And so how does this all come together on device? Well, when you go ahead and press the volume button and enter firing mode and you get your sights, the depth network is going to be from there continuously judging how far back you're drawing your arm, and it's going to respond with feedback, with haptic feedback based on how far back you're drawing. The harder you draw back, the more vibration and the more frequent that vibration is. And meanwhile, the gesture network is going to be continuously detecting if you're still drawing back, if your hand is still in a fist. And while that's true, it's going to wait to see when your hand opens, and as it does, it's going to fire that arrow, and you're going to exit firing mode and be able to rinse and repeat. And so how does this all come together in an overall system is that we have the input from the depth network and the gesture network. That's going into the phone. Meanwhile, we have these 3D models designed outside in an application called Blender. SceneKit helps with rendering these and assists in doing the physics calculations. SF Speech Recognizer is an iOS library used to do the speech recognition, AV Foundation for playing certain sounds, and UI Feedback Generator for working with the haptics. And so when and why does this system fail? And it definitely does, right? And so in my user testing, I found out that the network, it does not work at all on some people of a demographic that weren't well represented enough in training, whether it's body type or things like race. And even things you might not really think would affect the network, such as lighting conditions, can actually play a really big role, or maybe the color or shape of one's sleeve, for example. You could consider that the network, maybe the depth net in particular, could be looking at other things than just the fist, maybe someone's elbow position, and if it hasn't seen different kinds of clothing and all these different things that it would experience in the real world, you can get some really bad behavior. And what does this all come down to? It's that robustness is a problem with really large networks and with neural networks in general. If you don't have tons of accurately labeled, diverse training data, things may not work in production, and that's definitely the case here. And so how has this project changed over time? Well, it's changed a lot. I originally wanted to do darts with the Apple Watch, doing all this accelerometer calculation on device, but Apple's limitations, you can't run more than 15 seconds worth of a continuous process on the Apple Watch at a time. Furthermore, I wanted to do this in augmented reality, but you can't use the front and rear cameras at the same time. But other staff suggestions that I had, like haptics and sound effects, were really good suggestions that I got kind of the most positive feedback from the user study. And so thanks for those. And so what's at the next level, right? Like what's next to do? And I think that comes down to much, much more well-labeled training data, more speech commands, targets, game modes. And as much as this is all about intelligent multimodal user interfaces, the traditional UI still needs some more polish. So that's my project, guys. Thanks so much. And I think I'm answering questions now.